Okay, so I thought I would make a video to make this easier in case your Wi-Fi cuts out or it's easier to review. So just a reminder, we started the unit with intramolecular forces. So intramolecular forces was your ionic, covalent, and metallic bonding. Okay, and these are all true bonds. Now we're going to talk about intermolecular forces, which is really just a strong attraction depending on the type. Collectively, they're called van der Waals forces, and what intermolecular forces do is help us explain some of the properties we see. So the first one is the London dispersion force. If you click on this link, it is a simulation to show it. It is the weakest of all of our intermolecular forces, and it occurs in everything. So everything has this London dispersion force. And so the reason it can occur in everything is because electrons can shift around. And so here I'm trying to show this uneven distribution of electrons from the electrons just kind of moving around. And when they move around, you get a negative end and a positive end, and then you get this little attraction. And so it's just this uneven sharing of electrons. And it just happens temporarily. It doesn't stay, but it can cause a little bit of attraction for some point. Now, this particular force, and actually all of them, will become stronger when you have larger molecules because you have more electrons. It has to do with an increased electron polarizability and a larger mass of molecule. So that goes together. So again, this occurs in everything. Now, if we look at the next force, this one's a little bit stronger than the London dispersion force. If something has dipole-dipole, it also has the London dispersion force. Okay, so just think about if we're adding additional forces, it makes it stronger. So dipole-dipole, this link is a simulation for you to play with, and this occurs between neutral polar molecules. So the key is you're going to have two different molecules, and it has to have differing electronegativities. So we know fluorine has electronegativity of 4, hydrogen has one that's considerably lower. I don't remember what it is. Let's say it's 3.2. Because they have different electronegativities, it makes it polar. So remember, polarity is due to different electronegativities. And so what happens is the element that is more electronegative is going to pull those electrons closer to it, making it have a partial negative charge. This guy's going to have a partial positive charge because it doesn't feel the electrons the same. Now, because we have these partial charges, they're going to get attracted here. So that's what these lines are, showing this partial attraction between that hydrogen and the chlorine. Now, the more polar something is, so the greater your change of electronegativity values, the stronger that force is. Then we have our strongest force, which is hydrogen bonding. Now, make sure you realize it's not a true bond, it's just its name. This also has a simulation, and it is the strongest of our forces. Something that has hydrogen bonding will also have dipole-dipole and London dispersion forces. And you have to watch out that it's only hydrogen with FO or N. It's very specific. So you can remember this as hydrogen is FON, or in my AP Chem class, we came up with hydrogen FNO. So that means hydrogen bonding to F, O, or N, and I'm saying bonding as in it's attracted. And so alcohols will have this because they have an OH group, or you could say like HF or an NH or some variation there would have this partial attraction. And so if we look at this picture here of water, you have this positively charged hydrogen, negatively charged oxygen, and this is from that uneven sharing of electrons, and this is that attraction. And so what this does is, because this is a stronger force, you're going to have an increased boiling point. It's going to take more energy to break this attraction to make something boil. So these are the other things that hydrogen bonding is responsible for. That's why drops appear rounded on a surface, why liquids have a meniscus, capillary action, a film on top of a liquid surface, why ice floats in water, and why there's a double helix for DNA and RNA. So I have pictures of all of this. And so here's your droplets. If you had something like an alcohol, which its hydrogen bonding isn't as strong as water. It's actually not going to beat up the same. When we read the bottom of a meniscus for a graduated cylinder, that's due to sometimes our hydrogen bonding. Here's the capillary action showing the liquid going up the tube. Here's your water strider spider walking on like the surface of the water. Here you can see your hydrogen bonds with warm water. There's a lot of space in between these. With the cold water, it's getting closer, so now it's easier for these hydrogen attractions to happen. And then here you can see it becomes ice in that form. And it's very unusual for something to float when it's a solid. And then here's your helix. Hopefully that helps.